So hello together. Today I want to talk about the realization of a microstrip line low-pass filter. I will not emphasize on the filter design because I want to use my simulation tool to create a third order Chebyshev filter with a 0.5 dB ripple and a cutoff frequency of 1.3 GHz. And with the help of the simulation tool, we can create a transmission line filter. And in the later section, I want to emphasize then on the transformation of the transmission lines into microstrip lines. But first, I want to use now our simulation tool to do the creation of our transmission line filter. So I want to use now our simulation tool to create the transmission line filter, the transmission line low pass filter, and this is very easy to do. In our simulation tool we have a synthesis section, and here we can create a low pass filter. It's very important to see that we create here a low-pass filter which can be converted to a microstrip low-pass filter. So if I now open this dialog, then we use here the cutoff frequency we define with 1.3 GHz. The filter shall work with a characteristic impedance of 50 ohm. And we have a ripple of 0.5 dB. So if I now click OK, then we have here this TRL low-pass filter which can be converted to a microstrip low-pass filter. To check now the filter transfer function, I will include our network analyzer. I will connect now the network analyzer to the filter, and here in front of the filter elements are these elements. In front of this filter we have some short 50 ohm sections, and of course I want to change now our frequency range. We want to analyze the filter between 500 MHz and 3 GHz, and now we can do the analysis, but we want to have a look to the parameter S21. So this is our parameter S21. We can change the reference position, for example, and enhance the scale so that we really can now use the marker function to check if we have a 5 dB ripple here. So you see here we have the 5 dB ripple in the passband of the filter, and we will have a cutoff frequency of 1.3 GHz because here we have the same ripple. In a Chebyshev filter the bandwidth is defined by the ripple value, and then of course this filter will go down in the transfer function. We can also have a look to the parameter S11, and then you see here in the passband of the filter, due to the ripple, we will not have, so we will have some reflections in the passband of the filter which are due to the ripple here, and we have here the reflection will be around about 9 dB. So with the help of the simulation tool we could now do the creation of our transmission line filters, and in the transmission line filter we use transmission lines of different characteristic impedances, and the whole filter is designed for a 50 ohm for a 50 ohm characteristic impedance, and all the filter elements here will have the same electrical length, which is just lambda over 8 at the cutoff frequency. And now I want to use microstrip lines to realize this filter. But before we can use microstrip lines, I will give you a short introduction to the microstrip line. In this slide, I sketched the geometry and the electric field of a microstrip line. The microstrip line is essentially constructed using a certain substrate with a certain epsilon r, and this substrate will have a certain height. We will have a ground plane, and we will have a strip on the top which has a certain width, and the metallization will have a certain thickness. And the width of this strip will now have a certain influence on the characteristic impedance. So this formula is given here for the characteristic impedance, and this is you can find this equation, for example, in the book of Posar Microwave Engineering. And here I sketched the electric field. Of course, this is not an exact sketch of the electric field, but I want to point out here that parts of the electric field will go through the air region, and not all electrical field is concentrated in the substrate. Of course, this will have a certain influence on the effective permittivity which the wave which propagates on the transmission line will see. So the electrical length or the wavelength of the wave on the transmission line will be calculated using this effective permittivity. But we saw also that in the TRL section there are open transmission lines, and so we must now also have a look to the microstrip open circuit stub. So in the ideal case, the open circuit stub would be like this, so the electrical field lines would exactly end at the end of the transmission line. But this is not the case for a real microstrip line, but for a real microstrip line we also will have a so-called stray field at the end of the transmission line. And this stray field, for example, this can be described by a stray capacitance, or like in our case, we will describe the stray field by a certain length. So the transmission line, due to the stray field, the transmission line seems to be longer than its physical length. So if we realize an open circuit stub, we must account for this stray length, and this we will do now. So we can go on now in the design of our microstrip low-pass filter. Here we have the filter with the transmission lines, and the transmission lines are defined by their characteristic impedance and by their physical length, and the physical length is 1/8 of the wavelength at the cutoff frequency. So to convert now a transmission line to a microstrip line, we first have to include our substrate here. as substrate, we will use our telluride with an epsilon R of 2.33, a height of 350 micrometers, and disk metallization. So this is our substrate now, and if I want to realize now a microstrip line, for example with a characteristic impedance of 74 ohm, I can use our MSL design possibility which we have in our simulation tool. For example, in this case we would have for widths of 350 micrometer, we would have a characteristic impedance of 90 ohm. So we must use a broader widths now to reduce the characteristic impedance. So we can enhance now the widths. So we are now already at a characteristic impedance of 72 ohm, but we must use 74. So I will change the increment, and now we will go up again, and I change the increment again to exactly come to the value we want to have. So we have here now 7407 ohm as the characteristic impedance, and the width is 0.522 millimeter. But the length of 10 millimeter is not sufficient to get 1/8 of the wavelength. So what we will do now, I will change the length, or take a longer length. And now if we come to this value of 21 millimeter, we almost have done our job, but we can again change the increment so that we exactly can end up in 0.125 L over lambda. So this corresponds to 1/8 of the wavelength. Now we can replace this transmission line with a microstrip line, and the simulation tool will now use the designed values. So our transmission line of 74 ohm characteristic impedance is now replaced by a microstrip line of 0.52 millimeter width. And now we can have a look to the transfer function of the filter. This is the transfer function with the old element, and if I change now, do the analysis again, you see nothing did change. This means our microstrip line now exactly replaces our transmission line. In the next step, I want to change now the open circuit stub. Again, we use our MSL design, and then again we see here we must broaden our transmission line to end up in a characteristic impedance of 26 ohm. So we are here 2602. I can change the increment here, and then we exactly can come to this value. So we are very near now, but of course now, because we have a broader width, the L over lambda changed, so we have to change this again, the length, to end up in 1/8 of the wavelength. Change the increment again. So we are now at 1/8 of the wavelength, but in the case of an open circuit stub, we must account for the stray field, and the stray field is accounted by this additional length, so this length must be subtracted from round about 20 millimeter. So we now can change this here, and we include now an open circuit stub, and we must change the length now to 79 millimeter. So this gives now our open circuit stub. We can change this, and to prove if everything is correct, then we can do the analysis again, and you don't see nothing changed. This means our open circuit transmission line was now replaced by a microstrip open circuit stub. And of course, this you have to do with all elements. I did this before. And this is now our microstrip low-pass filter. And if we do the analysis of this filter, we exactly get the same values as before. And in the next step, I want to compare this with our measurements result. Before I compare our simulation with the measurement result, I have sketched here in the bottom of the slide our schematic for the simulation, and at the top we have here the realized filter. At the input and the output we have two 50 ohm transmission lines to solder the SMR connectors to our filter. One sees clearly the different widths of the stubs. So for example, this first stub has a width of 1.97 millimeter, and this stub a width of 2.5 millimeter, and here we have a very small stub. And of course, due to the different epsilon r, also the physical lengths of these stubs are different, and we have here the small transmission lines before the stubs, between the stubs. So now we can have a look to the results we measured and the simulation. Here the red curve describes the simulated results, and the dots are given by our measurement, and one sees a good agreement of simulation and measurement up to round about here 2.5 gigahertz, and here we have a certain deviation. This is maybe due to the fact that we did not incorporate, for example, T-junctions and so on. So this now finishes my talk. Thank you for watching the video. Your comments are welcome. Please join again.